Hello to everybody who's joining us on Twitch. My name is Carlo Barbieri, and today I will be presenting the new relational database connectivity functionality in version 12. This has been a very long road. It's been the work of almost 2 years, and it's a work that's been done in conjunction with other people. Those people include Leonid Schifrin, who is here virtually here with me, helping me answer questions you might have on the chat, and who you might know because he's written a very nice book about the Wolfram language before it was even called the Wolfram language. And the other person who was on our team during this project is Riccardo Di Virgilio, who has worked with me previously on interpreter, API function, form function, and a bunch of other cloud-related features. Okay, so why have we done this, and what we wanted to achieve with this project? First of all, I think, well, SQL is a very mature technology. It's been around for 40 years, and if there is a big data set, structured data set out there, it will likely be stored as an SQL database. There's been a little bit of a fashion of NoSQL databases in the past years, but it looks like SQL is here to stay. So some workflows have moved to, say, Mongo, which we incidentally do support as well, and I invite you to go see that Twitch talk. Some data, like from the semantic web, is stored as RDF stores in Sparkle, which are largely compatible with SQL, and which are also something we support. So go see that talk as well. I think it's on Thursday. But SQL is like really the giant here. And we're really excited to show you this, because it's really the first time that we have out of core data science capabilities in the Wolfram language. So in terms of design of what we did, we were in a kind of interesting situation, because many languages have what is called an ORM, which is an object relational model, which ties together objects in the sense of object-oriented programming with relations, that is tables on a database. But in the Wolfram language, there aren't really objects per se, and the Wolfram language is a mostly functional, symbolic language. So we thought long and hard about how to integrate that into the language, and we decided that the best way to leverage the uniqueness of the Wolfram language was to have a way to generate queries that was purely symbolical. And that is something that is extremely powerful, because it allows you to treat the queries before they're even evaluated as completely inert symbolical objects. You can manipulate them just as if they were data, but they are actually code. And so you can do all sorts of cool meta programming and constructing the queries step by step. And I think that is really something that we haven't seen in any other system so far. A part of this work is based on the existing functionality that is part of the entity framework, so the built-in knowledge base. But in order to be able to do interesting stuff out of core, we had to enhance the capabilities of the entity framework and add new primitives to it that correspond to common SQL operation, like filtering, aggregating, explicit joins. But I will show you more very soon about this. So first of all, I'm going to show you a very simple example that is basically just connecting to an external database. I've spent some time trying to find something on the internet that was public, and I found this interesting data set that comes from bioinformatics. So this is data and a public database from the Ensemble project. Contains a very large amount of data on genes and gene expression. And basically now I have connected to this database, and I have performed what is usually called an inspection. So I've looked at two tables. One is cross-references, and one is genes. And these that you can see here are the columns for those tables. So this is like an object that represents the schema of the database and all metadata related to it. Now, once you have that object that we put in the variable schema, you can construct an entity store. An entity store is a somewhat richer um, um, representation of the same type of information that basically lifts the SQL types, SQL tables into entity types, Wolfram language types, entities, and properties. So we now have two entity types, cross-reference and gene. And if you look, for example, at gene, you can see things like, for example, this gene ID property is bold because it was originally the primary key of the relational database. And so it becomes the canonical name of the entity. So there is a clear mapping between SQL concept and entity concepts. Then we can register the entity store. And now these entity types, xref and gene, become available for use on the in a Wolfram language kernel. So now, just to show you some kind of very simple first query, we're going to look at this cross-reference table, and we're going to count how many entities are in, which is equivalent to counting how many rows are there in that table. So I'm evaluating this. Now, okay, the first time is slower, but once you've established the connection, you can do this operation in 260 milliseconds. Now, if you consider that I am not geographically near the server and that ping time is going to account for roughly half of this, then you can see that SQL is really, really fast. Like this server is performing this operation of counting the rows in just, and there are over 2 million rows in just 0.26 seconds. Now, when I was talking about constructing the symbolical queries, now I want to show a simple example of this. So this example, I'm not going to go very deep into the bioinformatics because this is just meant to be illustrative of our syntax and not of the power of their database. So right now we construct this entity class. So I evaluate this and it doesn't do anything. Like it evaluates to itself. I just put it into a variable. So this is just an entity class. It doesn't perform a computation. It's just sitting there. And what it says is take the entity type gene, group the entities by biotype, and then count how many genes there are per biotype. Now, maybe, I mean, I've looked into this before, and there's a lot of stuff that is not particularly interesting, maybe biotypes that have only 2 or 3 genes. So another thing we can do is to take this aggregated entity class and sort it by count, descending order, and take just the first 10. And here, as you see, we're just constructing this query step by step. It's like just another Wolfram language expression. You can do whatever you want with it. It's not going to do anything. It's inert. It doesn't evaluate. How do we actually run the query on the database? Well, there's the function that we need is entity value. So entity value of this sorted entity class of an aggregated entity class will have some properties. Among those properties, we have biotype and count. So we run this and we get some data out. Essentially, we get two columns and because we selected 2 properties and 10 rows of data because we said here that we wanted only 10 data points. And then we can just take this data and plot it. And what it tells us is that most of the genes in this database are protein coding genes. Then we have, I don't know, processed pseudogenes, unprocessed pseudogenes. There's a bunch of RNAs that are like, this is microRNA, which apparently has very interesting role in gene expression. And so we have actually treated data that is fairly large on a database that is several hundreds of kilometers away from here, and it's completely public. And we got an insight about what kind of data was collected by this research group, which I think is like something that many people who use Mathematica in their day job or in research will want to do. Okay, so this is very simple. And I don't think it's a very instructive example other than showing you what the components are, because I mean, everything came out pretty clean. We didn't have to do anything strange. So I'm going to start with another example now, which I think is much cooler because it shows, well, first of all, it shows stuff that it would be impossible to do in the Wolfram language itself, because it's just too large a data set. And secondly, it will show some more real life examples of what happens when you deal with real data. So I was looking for interesting data sets, and at some point I found this thing which I thought was really cool. And apparently in the UK, any kind of real estate transaction is written down in a registry, which is a data set that is publicly available. This data set is actually a CSV file, so comma separated values, and is used as I mean, there is a nice script from the PostgreSQL website that you can use to import it in the Postgres database. It's fairly straightforward. So I did that. I'm not going to show all those steps with the terminal and command line because it's very boring, but I've already imported it into SQL, into Postgres. And now I'm going to do 3 steps that I did separately before at once, and I'm just going to register this entity store. So these are the last 25 years of real estate transactions all over the UK. It's, I think, a 3.5 gigabytes data set, so it's fairly large. Let's see how many transactions are in. The same trick we did before, we ask for the entity count. Now, this thing is running on my local machine, but it's large. So 24 million data points. Each of those 24 millions are a transaction which has a location, it has a county, it has a price that was paid, whether it was commercial or residential, all sorts of stuff like that. So what's the question you want to ask? Well, for one, we could ask, what are the most expensive cities in the UK? Run this, and if you look at this data, what I'm doing is basically I'm just asking for, so I'm aggregating, as I did before, by city, in this case, and I'm getting out the mean price of that city. And then I'm sorting in descending order, and I'm taking the first 8. So these are the 8 most expensive cities in the UK. And now if we take a look at this, we see that Gatwick has an average sale price. Gatwick is a place near London that has an airport of 18 million pounds. And the second closest is Thornhill, which is under 1 million pounds per transaction. So this is already something that, it's a bit fishy. So what we do now is we take interpreter, we run interpreter on these locations, and if the from alpha server collaborates, we get some geopositions. Well, let's pretend we got the geopositions all right. I don't know what went wrong there, but let's say these are the geopositions. That's just, I did this on purpose to prove that I'm really live and this is not recorded, because otherwise this would have been cut out. So we look at this, we can take a bubble chart of the stuff and see what it looks like. And as you can see, you get this huge bubble in Gatwick. So if you didn't spot it because of the scientific notation, you will certainly see it here, that this is like clearly 1 order of magnitude larger than all the other points. So something is not right, I think. So how do we check what's happening? Well, my first guess is that this is an outlier due to the fact that there are not enough data points for Gatwick. And to check my hunch, I do this, and then I'm like, okay, so this is like the entity class of all the transactions that happen in the city of Gatwick. I count how many there are. It's 7, but that's not good. 7 is not nearly enough out of 24 millions to have a relevant data point here. So we should probably filter out this kind of cities with low number of transactions and see what happens then. I just wanted to point out that I just ran through a list of 24 billion transactions on a file on my disk. I filtered out only Gatwick, then counted those, and it took a fraction of a second. And I think that's insanely cool. So now I'm going to do it again. I'm going to run this and see what I get. So now I'm doing the same thing, but the only thing that I did here is that when aggregating, I aggregated by, instead of aggregating just by aggregating by city and then just getting out the mean price, I also got out the count. So the number of transactions that there are. And then I filtered by the count, and I took only the places which had more than 100 transactions. And if you look at it, you will see that most of the cities that were present before are not present anymore. And so you get some more reasonable values. I'm going to, well, since interpreter didn't work properly the first time around, and I'm going to just copy this. So these are the geolocation that correspond to the cities, and we can visualize them. And they're all around London. Big surprise. So the places which have the highest transaction prices are all suburbs of London. And a fun fact that not many people know is that the richest suburbs of London are on the west. And that is the same for most European cities, even Paris. And if you notice, like the Versailles Palace is in Paris, is west of Paris. And some person once told me that this was because the prevailing winds go from west to east. And so this way, rich people don't have to smell the rest of the city. Fun fact. Okay, so this is where the most expensive places in the UK are, at least in the last 25 years. And now another interesting thing we can look at is what happens over time. So now we can clearly see that London is somewhat of an outlier with respect to the rest of England. And so what I'm going to do is to take the transactions that happened in the in the county of Greater London, and then I'm going to look at the transfer year. Now, for some reason, the dates in this database are not stored as dates. I mean, they're stored as dates, but it's a little bit complicated to get out the year. So what I'm doing here is just transforming the date into a string and then taking the first 4 characters which correspond to the year. And so these are the prices in London. We can do the same for all of England. So we just omit the filtering that we have here. And these are the prices for all of England. And then I can just plot them. And I think we already gained some pretty interesting insights here, because if you look at, okay, London is always like at least twice as expensive as the rest of England, of the UK, sorry. But what you see here is that the UK has a blip around the time of the 2008, 2009 crisis. And you can clearly see it here that in 2007, there's a maximum, and then it takes until 2010 to recover and go past that maximum. So 2008, 2009 are 2 years where the prices are going down. And you cannot really see the same in London. So basically, London kept growing, and there's like, it's almost stable between 2008 and 2009. 2009, but in 2010 it's already like gaining 40,000 pounds in value. And I mean, there are various theories about this. One that I've heard is that when there was the financial crisis, a lot of people in Greece and Cyprus were afraid that the government was just going to forcibly take money out of their account, and so they just blindly bought up real estate in other European cities, because it's something you can easily do in the European Union, and apparently um, this has actually had the effect of driving the prices up during the crisis in highly desirable um, uh, areas. So that this might be what we're seeing here. I don't know. Okay, so this is all I have to say about the UK, and I'm wondering if maybe Leonid has some question to send me, maybe not. If
no, not at this time, no questions, Carlo.
Okay. That can either mean that I've been not clear at all or very clear. Okay, so
I think the latter.
Thank you. So now I want to show something that is somewhat more technical, because up to now, I think it's not been very clear to anybody why should we use your stuff and not just go directly to SQL. Well, I think there are already a couple of answers to that. One is that this allows you to do hybrid, so kind of hybrid data science, where you first do the heavy lifting of data that is actually too large for your machine on the database, so out of core, and then once the data is small enough, you just take it into the Wolfram language, and then you have like amazing visualization capabilities. You have access. You can try to align your data to our knowledge base, and so you can like put things on a map or compare to the local population, which is something I haven't done here, but might be an interesting question. Like you have this data about the counties in the UK and their transaction. You want to know the populations, or you want to know the whether they're rich or not. You want to map against private schools, which are actually called public schools in the UK for some reason, and see whether higher real estate prices, how do they correlate with schools. That's all stuff that it's almost impossible to do directly in the database, but it's cool to bring it into the Wolfram language. But I think that where most of this framework that I use, ORMs and stuff like that are used to generate SQL, the place where they really, really, really shine is when they work around the most obscure parts of SQL, which most people tend to consider reasoning in terms of explicit joins. So if you haven't heard of it before, joins are an operation that we actually expose in the Wolfram language. It's called join across in the Wolfram language. And it's like probably the best way to describe it is like you take two sets and then you perform the Cartesian products between those two sets, and then you filter it in one way or another. And if you think that this is not a very simple explanation, it's because it's not a very simple concept. So what we try to do is to have a way to reason symbolically about how different parts of your database are connected together. And while this is something that described like this might seem like a very, very abstract concept, which requires us to introduce new concepts, we figured out that actually there already was a very close representation already in the entity framework that people were familiar with. And now I'm going to show you how this mapping happens and how this will make your queries much simpler right away. Okay, so let's take, so this is a small database that doesn't have much data in it, but it has a rich table structure. which was not the case before. And the cool thing about this relational database object is that it's completely like it's rich object that you can query. So for example, if I want to, if instead of opening this plus button and look inside, I can just evaluate this and what the tables that are present are. And say for each table, I can ask things like, for example, if they offices, I can ask for what the primary key is. Primary keys. Primary key. So this is the primary key constraint. It has constraint name. Well, it doesn't have a constraint name, and the columns that make up the primary key is the column office code. And then I can go and say, for example, offices, office code, and see what's, maybe I can do all here. And you get, so office code is, this is the types that SQLite use. In this case, it's a column of text of length 10. And then you have all sorts of interesting information directly from the database in a very computable way. And once you have that, you can look at all sorts of properties. So for example, another thing that we might look at is, so if I have this offices table, I can ask if it has any foreign key constraint. And turns out that offices doesn't have any, but like orders does have some. But this is like, this information is like really difficult to parse this way. So maybe one thing that I can do is, and now I'm going to explain what this means, is we can construct a graph object out of this. What this means is that basically, if you take, for example, the orders table, then that table has a foreign key to the customers table. It means that for each order, we associate one and only one customer. And then also for each payment, we associate only one customer. And for each customer, we have one employee, which is the sales representative for that customer. And for each employee, you also have a self-reference, a foreign key to itself, which is the manager of that person. And each employee is also associated with an office. So this is a very common way of structuring data in SQL. So instead of duplicating this data, you put it in a different table. So you have all the information about, so for example, you start from an order. You don't need to replicate the address of the customer, the name of their company, and whatnot. What you keep in there is just one single reference to a row in the customers table, and the customers table, you store all the data about that customer. So this is the way people think in the SQL world. Now, if you can work with that. It's not terribly complicated, but it's not as easy as we would like. On the other hand, if we construct an entity store out of this, something new has happened compared to what we had here. So if you compare the orders table, this is the stuff we had, and now we look at the orders tables, there are two new things which are underlined. These underlined things with a little arrow next to it are properties that we have generated for that entity type that point. So in the case of, so we are at orders, there's one that points to customers, and there is one that comes from order details. And that's what this does is something that will be familiar to some of you. And it's basically, these properties are going to be entity or entity class valued. And if you don't believe me that this is familiar, you can look at this. We take Steven Wolfram, and then we have a person entity. And if I now ask for notable books, wait, and we get more entities out. So in a sense, what we have here is exactly the same thing. We have the property customers, which is related to an order, is going to be an entity valued property. And then the sky is the limit, because these things, then each property is going to have other properties, and maybe those properties are entity valued themselves, and this allows you to traverse different tables. So let me show you how this works. So I'm going to register store, and then I'm going to show you what I mean. So now I'm taking the first entity out of the orders, which is the entity number 10,100, which is whatever random number is coming out of the database. And basically customers is an entity that has basically, that then we can query, and this is the customer corresponding to that order. And if you were somebody who worked with databases, bare databases, what you'd get out is something like this: customer number, which is just a number, and you cannot do anything with this. It doesn't have any property. So what you'd have to do is like join the two tables, then get out, figure out what the mapping is, how things have been renamed in the join, and then you can access the properties of each customer, etc., etc., etc. But why? And the other, if we look at the other relation in the other direction, what we see is that instead of getting one entity, we get an entity class. Why is that? Because if we know that for each order detail corresponds one order, we cannot really invert this and say this is just one thing. So we're going to have possibly multiple. So the order details are basically the lines in the order. So you have like an invoice and you ordered this many things. Each line in the invoice is going to have an amount of things and a product that you bought. Okay, so and basically once you have this entity class, you can actually verify yourself that this is made of many things. And so these are all the items that were bought. So why is this powerful? Well, let me show you something. So basically now I'm asking this question. I'm taking one customer, and out of this customer, I'm figuring out who is the employee, so the sales representative of that customer, and what their first name is, what their last name is, who their manager is, and who their first and last name is. So in this case, I run this, and this generates this result. And if you think that this is like some kind of monster, you're wrong, because this looks kind of complicated, but it's just a template, a string template that I'm building. And there's actually a trick if you want to see what's actually getting executed on the database, which is $db query logger. So we are going to log what's being done here and run this. You get this SQL monster. So basically, there's a bunch of nested selects. There's subqueries involved here. It's very complicated. You don't want to have to write this by hand, but on the other hand, this is just functional composition. It's like accessing subparts. It's very natural. And it's just as efficient. It's something that's getting executed into a single query. So how would you normally do it if you didn't have access to this? Well, there is this, the construct, like the translation of this into a Wolfram language query would be to build two combined entity class, which is what corresponds to the join in SQL. And then you have a pretty similar entity function. But this part is part that is really difficult to reason about. And if we look at this, even in this case, the SQL is not very short. It's not really, but in this case, it's like closer to the length of the Wolfram language code. So this is, I think, where like using our stuff really outshines writing bare SQL, because then you can actually reason about basically entities and properties as if they were subparts of an association, and you can follow the links on this graph just as easily as adding another square bracket and say, oh, but I wanted so what we did here was like we really started for customer, we found out who the sales representative was, then we found out who the employee, so who the manager was, and then we're extracting information out of this table, and then again out of this table, but another row, in a single query, without having to perform a single join, without having to reason about joins. And I don't know, I just think this is really, really cool. Okay. So if there are no more questions, I think at this point, I want to close with something that is actually really, really impressive and which might take a little bit longer to evaluate, but I think it's worth it, because I'm going to show something that is definitely not something that I could have done on my local machine. So I'm going to connect to a database that is on an actual server in the, I think it's in Champaign, in our headquarters, that contains the whole dump of OpenStreetMap. So OpenStreetMap, in case you don't know, is like so the Encyclopedia Britannica is to Wikipedia as Google Maps is to OpenStreetMaps. OpenStreetMap is a map of the world that is user-generated, user-contributed, open source, anyone can use it. Most of the original data in Apple Maps was taken from there. It's a really cool project that has been evolving in the past few years, and it's a really massive data set because it contains all the roads, all the points, all the sports facilities in the world. So this is, I connected to it, I registered the entity types. Let's see how many points are in just one of the tables. And it might not be exactly quick, but it's not even too long. So in the whole data set is about 1 terabyte completely. And then the stuff we're going to query is of the order of several hundred gigabytes, if this works. You have to make sure that I am on VPN, so that I'm connected to the Wolfram Research headquarters, and I can actually query this database. Actually, last time I tried this was a few days ago, so maybe, I don't know, credentials have changed and nothing is happening here really. Hold on tight. Okay, let me start. Let's see. Okay, so I'm gonna re-register this one. It's gonna complain that it was registered before. And now I'm gonna run this again. But I mean, this thing should complete in a few seconds because it's just counting. But if it doesn't, then I'm gonna have to drop this example for today. Maybe the server is down or something like that. Actually, I have a way to check if the server is down. I can just say database connect to RDB. And if just connecting to RDB takes a while, then it means that something, okay, let's disconnect. Disconnect was quick. Okay, let's try again. So what I'm trying to do here is to run through a table that is 200 gigabytes and figure out how many rows there are. The answer is going to be around 4.7 billions if nothing has changed, but maybe they changed something on the database since last time I tried, because this is a database that is under active development, which is something we use for our GIS functionality internally. So every time you see a map or you query interpret street address, what we're using is actually data that's coming from OpenStreetMap. So there is people constantly working on it. Okay, so this is not collaborating, and I don't want to bore you any further. I'm gonna show you another example. Let's see if this one works. this is like I'm asking now. So I'm creating this table that's called OpenStreetMap line, which contains all sorts of one-dimensional things. In this case, I want to know what are among these lines, which are mostly roads, which contain the word Wolfram, ignoring the capital W. Okay. I think the server is just not responding today because last time I tried this, it took like 10 seconds, maybe 5, and this has already passed. So maybe something else is going on. Anyway, I hope you believe me when I tell you that I already tried this. And if you go to the marketing page, you are going to be able to see all sorts of cool stuff, including at some point I just ran this thing where I was looking at all the sports facilities. I'm just going to paste it here to show you. So basically, if we look at the sports facilities of the world that are mapped, then we get this nice word cloud. There are like something like 11,000 swimming pools mapped throughout the world, and 9,000 soccer fields, and then 8,000 climbing locations. I mean, I found it pretty surprising that there are so many climbing sports facilities and so few volleyball sports facilities, but maybe, so this finished running. I got all the streets in the word that contain the word Wolfram. So there's that. Now you can believe me that this works. This is the generated SQL because I didn't unset that variable with echo. And so you can see that this is kind of interesting. Like each database backend has a different syntax for doing regex. And this is the one for Postgres. So yeah, I think this is what I wanted to show you. Maybe one last thing, since this has worked, how many trees are mapped in the OpenStreetMap project? How many single trees? 11 million trees throughout the world. So there's somebody somewhere has just gone there and said, oh, there's this tree next to my house. Let me put the GPS coordinates in this open source project, and so that everybody in the sea can have a detailed map of the world. I think this is just awesome. And the fact that we got this answer in just seconds, maybe 2 or 3, is also awesome, even if this database is on the other side of the world. So that's it for me. Do we have any questions? So the question is about SSH, and there is a tool called MySQL Workbench where you can fill in the details of the SSH connection and the server details. So actually, the way it works is when you connect to some MySQL server or whatever it is, there are 2 ways to enter this information. One is by saying relational. Well, you have to put it into a relational database, and you can just do something like MySQL and then I don't know, localhost. Well, I actually have one that I was showing before from my own machine. Which was exactly MySQL. It's another of the examples. So for example, I installed on my own machine a dump of Wikipedia. In this case, so this says the protocol is MySQL, username is username, password is password, at localhost. I'm not putting in the port because I'm just using the default one, and wiki is the name of the database. So if you can either use this, what is called magic string, which is standardized more or less across backends. And the other thing you can do, no, it's called database reference, is if you, and I'm going to use a trick here. I'm just going to parse this string and show you the full structure of this, which is this. So if you don't want to fill it in that way, you can just say backend goes to MySQL, name goes to wiki, it's the name of the database, port goes to none, host goes to localhost in this case, username goes to username, and password goes to password. And I mean, we don't have a widget to do that, But it's a fairly simple exercise in the Wolfram language to construct a form function that does exactly that. So basically, all of these fields are strings. You might want to mask the password, but if you want to do that, you just do, okay, this is going to be, you take the first argument of this, which is an association, then you take the keys out. What's the problem with this? No, I said
the input
first.
form is a problem, I guess.
Yeah. Okay, so you take out this list of strings, and then you want to do something like association. No, well, you don't even, yeah, association map of, well, actually, you just need string 1%. So this is going to be your association. Maybe you're not happy about this. You want the password to be masked, and so you can say something like interpreter goes to string, and then masked goes to true. Then you close this association, and you just say form function of this, and you get a widget to input this stuff. The password is correctly masked. It's missing, it's missing the port, but the port has a default. So I can just say port goes to, and then this is going to be an integer. And I don't remember now, 4432, something like that is the default for MySQL. You do this, and then you have a port here, and it will work even without submitting it. Then in the body of the form function, you are going to put something like database reference of this association that's coming out, and you're going to get exactly what you'd expect. So, okay, we don't have a point-and-click widget, but it's in the Wolfram language, it's a one-line exercise to write it. So I encourage you to do it yourself if you like it. I'm sure that Mr. Huisman here is a knowledgeable enough user to be able to do something like this. Okay, so since we're a geographically diverse company and I am based in Italy, here it's 8 p.m. So it's my dinner time, and I wish you all a pleasant afternoon or evening or morning, depending on where you are in the world, or if you're watching a rebroadcast of this thing on Twitch or on YouTube. Thanks, everybody. Thanks, Leonid, for shadowing me. Thanks, Ricardo, for writing the code. And bye-bye.